All right, sports fans, this is our part 2 of the test review for force and momentum test. We're going over the 5 problems on the back part of the exam, questions 1, 2, 3, 4, and 5. The first 3 questions use Newton's second law. I want you to notice that I've taken Newton's second law, and the first question solves for force, the second one solves for mass, and the third one solves for acceleration. That equation was already manipulated for you. All you had to do was plug the numbers in. So let's practice this. The first one says, how much force is needed to accelerate a 90-kilogram skier at 3 meters per second squared? Before you get all lost in everything that's asking, step 1 is, what do they want you to solve for? Well, force. Step 2 is, do we have a relationship with all the variables or an equation that teaches us about force? We do. It's right there. So take the time to write down the equation. Force equals mass multiplied by acceleration. I know it's right there, but write it anyway. Step 3 is now plug in the pieces that they give you. They give us a mass of 90 kilograms and an acceleration of 3 meters per second squared. So we'll plug it in. Force is equal to the 90 kilograms times the 3 meters per second squared. And so now this part is relatively simple math. Use your calculators if you need to. Force is equal to 270. But remember, half your points come from deciding 270 what? What are the units that go with it? If you remember that force is always described in newtons, in our class at least, then you can get those points there. However, some of you were smart enough to say, I took kilograms and multiplied it by meters per second squared. You could also say 270 kilograms times meters per second squared, which is actually what a Newton is. So either one of those will work. That's your answer for number 1. Let's move on to question number 2. Question number 2 states right here, what is the mass of an object that requires a force of 30 newtons in order to accelerate at 4 meters per second squared? Well, what do they want us to solve for? In this one, it's mass. So we write Newton's second law, but in this case, we're solving for mass. So it's force divided by acceleration. It's the same equation, it's just rearranged to solve for a different variable. Now we plug in what they give us. They tell us here that the acceleration is going to be 4 meters per second squared, and the force is going to be 30 newtons. So in order to solve for mass, we take the 30 newtons that are applied to get an object to move, 4 meters per second squared. And now we're back to this plug and chug idea, relatively simple math. We can figure out that the mass is going to be 7.5 when you plug it into your calculator. But 7.5 what? If you remember mass in our class, we always start off with kilograms. Then you can put the label there and be done with it, right? Some of you put newtons over meters per second squared, and I can't argue with you. Technically, that's not wrong. It's not simplified, but it works. That's question number 2. Question number 3 asks us to solve for acceleration. They say that the object has a mass of 12 kilograms, and a force of 5 newtons is applied to it. So here's the equation, Newton's second law rearranged for acceleration. Let's get a clean board, and we'll show you how to solve for acceleration. In this case, acceleration is force divided by the mass of the object, right? You can't solve for acceleration using this equation if they don't already give you force and mass. And in this case, they do. They tell us that the force being applied is 5 newtons and that the mass of the object is 12 kilograms, right? So let's go to our calculators for this one. 5 newtons on top divided by 12 kilograms on the bottom. That's our mass. And we end up with this number right here, which needs to be simplified. Go ahead and keep 2 digits past the decimal place. So 0.416. The 6 requires us to round that up to a 2. So our answer is going to be 0.42. But 0.42 what? We need a label here, right? We solved for acceleration. A lot of you just remember now that acceleration for us is in meters per second squared. Okay? But if you couldn't remember that and you went back to the equation and said, well, I had newtons over kilograms, so I'm going to put my units as newtons over kilograms, although not simplified. I gave you credit for it because I thought it was a good use of the units in the equation. Okay? Those are the first three using Newton's second law. The numbers will change, but the process most likely will not. Here is question 4. Let me clear the board for you before we start talking about this one. It's a free body diagram. Remember, our free body diagrams require us to look at the forces that are acting on an object at that very moment. Okay? Not the movement, not the direction it's going, but just the forces acting on that object, and we get to use arrows to represent those forces. So here's what's going on with number 4. A free body diagram, there's a book, it's being pushed on the table, and it is accelerating. Label all forces. Looks like a regular, normal, not so bad free body diagram, but there's a lot of points here. Our book, go ahead and draw something to represent the book. Could be a dot, could be a triangle. Well, I don't know. You choose any object to represent the book. Okay? I like to start with the forces that are vertical, and then I worry about horizontal. So this book is on planet Earth. We know that there is a force down, and that's the force of gravity pulling on the book. But it's on a table, so there has to be a force upward that's keeping gravity from making it fall down. And that, for us, is our normal force. Okay? The arrows should be pretty close to equal because the book is not accelerating up or down. It is accelerating either to the left or to the right. So the book is being pushed. So I'm going to draw an arrow representing the fact that there is a force push. And there's friction in the opposite direction as it slides across the top of the table. But that friction arrow should not be as long as the force push, because the book, it says, is accelerating. And if it's accelerating, we know the forces have to be unbalanced. You can't have a net force of 0 and have all your forces cancel out and still have the book accelerate. Okay? So that one's number 4. The very last one, number 5, says right here, draw a free body diagram for a book that is in free fall. There is air resistance. Okay? So it's in free fall, being pulled down by gravity, and there is air resistance. So here's how it looks. Our book here, let's go ahead and draw a rectangle for that. Since we're on planet Earth, we've got to draw gravity. Okay? There is the force of gravity down. And it says that the book is in free fall and there's air resistance. Air resistance is a form of fluid friction. It should be up, right? Friction, you could call that even force air, right? You name it. I'm not too worried about exactly what you name it as long as you identify what it is, okay? Now, there are a couple ways you could have drawn this a little bit different. The book could be falling and accelerating. In that case, your gravity arrow would be longer, okay? One thing that lost a few of you some points the first time around is you made the force of air really strong going up, stronger than friction going down. There are some circumstances where that's possible, but not the way it's described in this problem. Okay, so you get a point for each arrow and a point for each label. So this one was worth 4 points. The previous free body diagram was worth 9 points. Okay, see if that flushes out any questions. You've got 1 week till next Friday, which I believe is the 29th, to go ahead and do a test retake. Good luck.